So welcome everybody. So we have now a very interesting session on, well, first one on the Quantum Simulation Research Unit. And it's my pleasure to introduce the first speaker in this afternoon session, who is Tilman Esslinger from ETH Zurich, who will talk about emergence of topological pumping in atom-light interaction.
Thank you very much for the invitation, and it's a great pleasure to be here and see the Munich or the wider Munich community. Very good. So let me just directly start and let's maybe start with a view a little bit into the future. Maybe some of you have already wondered what will it be like to be a physicist if we do have quantum computers. I mean, what does that mean? How will we live? And because I think we should not only think about what can we do for the quantum computer, but we should also think a bit about what can the quantum computer do for us. Because, I mean, we will be the first who will use quantum computers. So let me show you a wish list for the quantum computer from a physicist's point of view. So, of course, my own wish list. So what I would like to have is a machine. I give an input many-body Hamiltonian. I write it down like a theorist. They write down Hamiltonian. So I write one down and then put a many-body state in. And then I want this machine, this quantum machine, to do the evolution for me. And then I will get output. And there I actually want to have surprising results. That's really what I want. I mean, I want to discover new phenomena, and then ultimately I want to have microscopic understanding, and then maybe generalize. And then, well, in the future, I would also like to build devices with them, with this many-body state. So that's why I'm a bit, for me, a pure quantum computer is almost a Papiertiger, because it's the many-body state is not really there. Anyway, in this spirit here, I want to focus on the surprising results. And I want to talk about basically 3 view graphs, 3 data sets. And this is the first data set where we saw a step in a phase of our experiment. And we did not expect that. We just saw that. When it was first time shown that we've measured these nice steps, my spontaneous reaction was, it looks like a quantum Hall effect. It was not too bad, not too far off, even though we were not looking for a quantum Hall effect there. And then that also brought us, I mean, conceptually there is a link to that, to the topology and interactions. There we found out how can we build a topological pump that is super robust. And super robust means that you can put trapping potentials there, you can put interactions there and see what's happening. That is the middle one. And on the right-hand side, there we are still in confusion. That is a result about a nonlinear transport phenomena in the vicinity of superfluidity, or with a superfluid present, but where the superfluid leads to a large entropy transport, which is a bit contradictory. Okay, let's start with 2 kind of little background slides, or 2 topics with some background slides. So that the first one is topological pumping. Quite a few of you know that because there had been quite some work in Emmanuel and Monika Eidelsberger group. So the basic idea is you take an optical lattice and then you take an optical superlattice with a larger, double the period, and then you can imagine that your band structure will split into 2 mini bands So this band structure will split into two mini bands, and then you can fill the lowest mini band, so it's an insulator. And now when you move this larger, the longer wavelength potential, then you will see that in sync your whole band insulator will move. You can also look at it, so you can transport an insulating state. You can also look at it in a wave function picture. Let's say you have on one side a wave function delocalized here, and then you shift this one potential with respect to the other, then you adiabatically transport the system. And you can look at it in terms of topological pump. So what you mustn't do is you should not cross the zero here, because then the gap closes, and then you mix the lower miniband with the upper miniband. But it's simply a double wavelength versus a wavelength moving. Okay, and now, and then also, which is maybe one does not always remember, that the lower miniband moves into one direction. If you put the particles in the upper miniband, then they move in the other direction. And now something seemingly totally different. That's the optical properties of a Bose-Einstein condensate in an ultra-high finesse cavity. And now look at this Bose-Einstein condensate as a superfluid refractive index. That's the simplest. So it like a glass window, and then you can shine light on it, and it will pass through. But now you have a cavity in addition, and then we would say, okay, the light will still pass through. However, if you increase the intensity of this light beam, at some point, the system will scatter light into the cavity. And then you wonder, why? The reason is, if there is light in the cavity, the system can lower its potential energy, because it's well, in this case here, red detuned light. It can lower its potential energy, but it has to come up with a ripple. And here, of course, you see the ripple is exactly such that you have a refractive index ripple, such that you get Bragg scattering into the cavity. But that costs some energy. But once this energy is less than the energy that's gained, you have a phase transition into this structure, and there is a symmetry breaking between even and odd symmetry. One can also map that to the decay model, but here this is enough. Okay, and now let's come to this data set with these funny steps. And the funny steps, you see here is the laser power plotted. So that's the laser power, the incoming here, and then partly it's reflected here, and there's a 60-degree angle. And this phi is this phase of the light in the cavity, and it's measured with respect to this pump light. So you switch on that, and suddenly you get this funny step. Okay, that's how our quantum simulator looks like. That's what you will say, it has a cavity, so it's not a closed system, it's an open system. So that's what the open system looks like, a bit more complicated. And most importantly, of course, the team. There, Tobias Donner on this experiment, he's co-PI, and that's the team working presently. And Alex Baumgärtner just got his PhD 2 weeks ago. Okay, so what did we see? So the first thing, and that already was a bit of a surprise. Well, we thought, oh, let's do it a bit different to the previous experiment. Let's go to blue detuned. Maybe one can also see self-organization there. And we saw what we expected, this crystal 1. But then there was also, always it was said, we have this strange background scattering. And at some point we thought, yeah, what is that? I mean, this background scattering is this. And that turned out to be another phase. So what, and I now be quick here, what turned out here, you have two two crystals. It can self-organize in two different crystal structures, and they have two different centrosymmetric crystals, each one breaking a Z2 symmetry. For the optics person, it means, okay, you have the light, you shine on the BEC, and then you measure the phase coming out, and then this relative phase can either you have a plus minus sign, or you have a plus pi half or minus pi half. So it can couple at the two possible quadratures of the cavity. And that then corresponds to these different crystal structures. And then, of course, we thought, now so what you see here is the light intensity coming out of the cavity, and here is a phase of measured, as I showed you on the early graph. And then we will ask the question, what happens if we move across here, from here to here, and then we could see, this order parameter, which is basically the phase of the light field coming out, or the light field, that changes its phase and in a little bit of a dynamical way. So kind of a first order transition. But that was done in a regime where the detuning, where dissipation didn't play a big role. But we had another cavity in the system with a larger dissipation. And there we saw something different. There suddenly, this second phase seemed to take off. I mean, that moved away. So it was a bit scary. And then we fortunately looked in what is actually happening here. And here we measured again the phase. And here the phase showed these steps that I showed you on the early view graph. And the difference here now is that dissipation in the first case didn't play a role, but here now dissipation plays a role, and it couples the two quadratures of the cavity light field. And with this, it leads to a rotation of in this quadrature space, and to periodic change between different crystal configurations. And we do that while we increase the laser power, and then it stops again. And so it comes from one order and then does this oscillation and ends up in the second order. And here we can also see, well, when we measure the phase quantitatively, it always goes from zero phase, of course, a zero somewhere, a phase we have to set, a zero. And then it goes to 5.5 or 9.5, 6.5, 3.5, always something plus a half. And that was during Corona time, so we had a lot of time to think what is going on. And we could also measure, we could see that it does a winding in this, that is the space of the quadrature of the light field. And the final solution of what is happening is that if you look at your light field that you create by scattering this self-organized crystal, it has one component which has a short wavelength, and it has another component which is phase-dependent in this configuration, which is phase-dependent, which has twice the wavelength. And if you now look at what is happening when you rotate the phase, but the system does it itself, then this pattern is moving with respect to the other pattern, and it looks like this. So you get a pumping mechanism from the system itself. And we can also, then we checked, does it do the right move, does it move in the right direction? So the pump is in this direction and the movement is perpendicular. And if we take the other cavity geometry, it's moving in the other direction. And the movement, the center of mass movement of the cloud, it always goes with a number of windings. So it might speed up, but it goes with a number of windings. So this is, in a way, an adiabatic pump, but the question is who turns the handle, and there the system turns it itself. It's a dissipation that is coupling the two quadratures. And, well, it was Corona time, so one has time to think, and then one thinks, but usually for this topological pumping you need a green and a red laser, and that's a bit painful, but it seems to work with just one laser frequency. And so I then thought that it must also be possible to implement the scheme in our fermionic experiment. And indeed, there we have this tunable geometry lattice, and there we can implement, by not perfectly retroreflecting and controlling with one set of phase control beams and letting the phase run, then you can also get this topological pumping configuration. So it's one lattice with a large spacing moving on top of a smaller spacing lattice, and then you can of course choose your tunnelings between the different lines as you wish. But that is now, then we thought, let's try that, and immediately we saw, whoop, it's perfectly pumping. And just to remind you, here seems to be that some of the atoms were in the upper miniband, and the upper miniband is moved in the other direction. That was this. And from an experimental point of view, and having done Floquet physics, the nice thing here is that all physics is happening in these two lower minibands, and all the frequencies are low compared to the higher bands. Usually if you do Floquet driving, you couple virtually to the higher bands, and that causes problems when you have interactions. But this should be robust to interactions. So we thought, let's see what, let's try. And that comes to this picture, the second picture. And what you see in this picture, let me make it a bit clearer. It's many, many pictures. And we repeat the experiment and do this transporting longer and longer and longer. And what we see, okay, it transports. And then it seems to get stuck, and here something gets reflected. I must say, it's in a trap, you will see in a moment. And then we see something happening here as well. Let's first look at what's happening when you have the trap. So it's a topological pump, but in the inhomogeneous trapping potential. And there one can, it is, if one thinks a bit, then it makes sense. Even though some people said, it gets stuck. But in reality, it's the systems are reflected back. So what is happening is, well, remember here it's this basic pumping scheme, and what is happening now in this parameter space, so that would be for homogeneous parameter, but if you do a kind of a local density, then your delta is getting smaller and smaller, and that means this circle moves up and up when you go further into a stronger and stronger gradient of the trap. And then suddenly you're circling, you're no longer encircling this central point, and that's when you couple between the lower and the upper miniband, and then it's transported back. And here, since these states get, this delta gets smaller and smaller, these states get more and more localized. That's why you have this slow decay until they are transported back, because they get more and more localized, these states. That was without interactions. And you can look at it also here as that you have a topological boundary formed by the trap, which is here, and that's where you couple between the lower and the upper miniband. And you can also you can express it in terms of Chern markers, which go to 0 at the gradient. now let's look at repulsive interactions, because this is interactions. The system is happy with interactions. And here that was the other data that I've shown you. And now we zoom in and take many more measurements, what is happening here. And there we can see a good part of the cloud is transported, just topological transport, but then parts are reflected back earlier. So it's like an additional topological boundary due to interactions. And that also makes sense, because now you have, besides this delta as an offset, you have an additional energy scale, which is U. Now you can imagine two repulsive particles on a side. They will hybridize with the next higher miniband. And that means at that point, let's see, yeah, here it's shown. So this doubly occupied side comes, so with a spin up and spin down, and then it hybridizes. One will continue to go further in the same direction, the other one goes back. And they should be, that we have not yet kind of measured the bell pair, but it should be a production of bell pairs, one going to the left, one to the other one, and with random spins or correlated spins. And, well, this is the lab, and most importantly, this is the team, and it's led by Konrad Fiban. Let's move to the last view graph. Ah, yeah, 5, that's good. And this, what you see here, is a delta n, well, more precisely delta n over n, and a delta s, an entropy. So we take advantage in these measurements of the fact that in cold gases you can measure entropy, and in your reservoirs, but you can also measure the transport of entropy, because you can have two reservoirs and you couple them, and then you can measure the transport. So, and that's what we did, but step by step. So how do we do that? So that's we start with an elongated lithium cloud, and then we shape it into these two reservoirs with a channel in between, as is shown here. And so, yeah, so it gets narrow and narrow, this channel, when we have enough laser power. And then we have kind of a control by this red beam that basically we call it gate beam. It gives us what is the energy offset of the potential there. And yeah, the experimental scheme is fairly simple. You have, say, more particles on the one side, and then you open, and then you see what's happening, and then the particles are flowing to the other side. Which is, yeah, quite straightforward. And then you take a picture how many particles, and then you repeat the usual thing. That's what the cold atoms people do in their labs. They repeat. And then you can see that you get an exponential decay of this imbalance. That's exactly what you would expect. And you get a time scale for that. And if you do a little bit of calculation, then the time scale is given by the compressibility divided by G, that's the conductance, and it's a kind of the number of channels that you have. And of course, when we did those first experiments, and people asked, can you also see quantized conductance? And yes, if we have a narrow enough channel, we can see quantized conductance. But where we saw the surprise, that is the team, very important. And that's Miles is a postdoc on that, and we have a long-standing collaboration with Thierry and Wilhelm, and Wilhelm Zwerger, and also Jean-Philippe Prantu worked on that experiment for a long time. And now we are looking at the same setting with unitary Fermi gas. Okay, so it is a paired system. Here in the center we are superfluid, here are further outside not. And then what we see is we see these nonlinear decay curves. Let's focus on the red and the green. And one can wonder, why should that be nonlinear, or how should there be transport anyway? Shouldn't be there a Josephson oscillation, but we see directed transport, so we need something, some means why it's directed. And the mechanism we believe is our multiple Andreev processes. So kind of you have a very small delta mu, much smaller than the gap energy, but if 5 pairs go, then you can break 1 pair energetically. And yeah, you can imagine here, so 2 comes, 3 are coming, 1 is breaking. So now the chemical potential goes lower and lower, but still you have a large current. You can break one of the pairs which jointly go. So that's just an impression what this mechanism is. But that we knew already. But somehow we thought, but let's look at what actually, how much entropy is transported in this system. And there we saw the entropy curves, they just looked almost the same. And then we could say, okay, well, how much entropy per transported particle? And that on the one hand, it was always the same. It was always 1.18. And it was robust to the power. It was robust and it's large. I mean, with superfluidity, you don't expect transport of entropy. And then we also did not just change the relative atom number, but just the relative temperature. And then we saw a very rapid response and then a super slow response, an almost steady state, this red curve. And so we have clearly a nonlinear behavior, and we have 2 transport modes for entropy. One is an advective one with a number of particles and a diffusive transport. We can model that with when we extend the linear transport equations with an additional nonlinear response, which just, well, there is some theory where they do this nonlinear transport equations, and with that it fits extremely well, but it also means that it's not described by a 2-fluid model. And we have no clear microscopic picture. It's just clear that there is there must be a nonlinearity. And with this, I think all the team, and I've not talked about the cavity, even though it's fun stuff they are doing. But anyway, I thank them all, and I thank you for listening. And this is, the green stuff is what the future direction, but let's stop here.
Thank you very much for the very nice talk, and we have some time for questions. Questions? Maybe I can start. So regarding the pumping experiment with repulsive interactions, is there any hope to detect this entanglement that you predict between both parts of them?
You mean where we produce yes. I would say yes. I think it shouldn't be, I'm hopeful. Yes, I look at it at the moment. It's really a source of these pairs, and one should be able to detect it. Yeah, we are working hard.
Okay, thanks a lot for the talk. First slide, it was very interesting to hear that we do not need a quantum computer to develop a quantum computer. That would have been an interesting suggestion. And regarding to your talk, with these 2 containers connected by a narrow conductance channel, for superfluid helium we have the thermomechanical effect. Would you expect something similar for such kind of system?
What effect?
Thermomechanical effect.
Yes.
When you are heating up some container, you are having...
It is related, actually. You can rephrase a lot in terms of thermoelectricity or thermomechanical. But we were then surprised, and we had done some thermoelectricity, and one gets high numbers, so for applications, fantastic, but of course, these systems. But then we were very surprised to see this, that we have a large entropy transport, that we simply did not. When we looked at the entropy, the picture was different.
Okay, so that means that it cannot be described as a simple two-fluid model as
no, it cannot.
helium.
No,
Okay.
no. This nonlinearity, that is a nice thing.
Okay.
Yeah, yeah,
Okay.
yeah.
Oh, great.
Yeah.
I also had a question about the last part. Would it be possible to have different interactions in the initial and final state reservoir?
In the initial and the final, yeah. Now, changing the interactions, that's what we are doing, the BEC, BCS crossover, but different ones in the initial and final, it's good. Maybe one could do with another spin component. Yeah, no, that's a fun question, yes, yeah. Well, think about it, yeah.
Okay, so for the sake of the schedule, I think we can stop here and defer further discussion to the breaks. Let's thank Tilman again.